Car. Let's say we have a car that does the diameter. What do we not like about diameters?
Thank
you. The diameter of the circular track is 100 meters.
So 50 meters.
Thank you. I would like to know the velocity. And what is this velocity, by the way? Radial or centripetal or tangential?
Tangential.
It's tangential. So when I'm twirling a yo-yo,
Let go, we'll go in a straight line.
that's that part out. When I'm twirling a yo-yo and the line cuts, the tangential velocity is the velocity of the keys going off in a straight line. Thank you. So that's that. So let's say his velocity is 20 MPS, meters per second. We're good? I would like to know the coefficient and what is the force pointing back to the center before we go any further? It is friction. It is static friction, surprisingly. A lot of people think it's kinetic. I would like you to find the coefficient of static friction
Friction is what?
given that information. Okay?
Friction is
Let's do that part first.
You got 0.8.
0.8 for a coefficient of static friction?
Yes.
We're good?
Yes.
Yes.
Okay, how did we do that? Whenever you see a circle, FC equals mv squared over r. What is supplying the FC?
Friction.
Friction is equal to two letters,
UN.
UN, and this car is not on a bank, it's horizontal, therefore N equals
MG.
mg. So I'm thinking UMG equals
Friction.
mv squared over r. What do we not need? The mass is canceled. I gave you the velocity, 20 squared, 400. Solve for u, 0.8.
Planetary motion.
Planetary motion.
To the satellites.
Let's say I got planet X.
Geosynchronous orbits.
It has a mass 1/3 the mass of Earth. It has a radius, that's supposed to say 1/3, 1/2 the radius of Earth. Okay?
What?
I would like to put a satellite in geosynchronous orbit. Is it moving?
Yes.
Geosynchronous sounds like it's not moving. Is a geosynchronous satellite not moving?
Yes.
No, it's just
But it's
above the same spot on the
It is moving, but it's moving with a spot that it is continually over.
question.
Does that make sense?
Yes.
If it's not moving, the planet is, therefore it's not in geosync orbit.
It's like the moon.
Yeah,
The moon is
No,
isn't it?
I don't think so. It has a different rotation than, its year is different than ours. If it was in geosync orbit, Zach, it would stay above Hawthorne and appear to not move.
Oh.
It would move with us.
So it would be
But
like
it does.
double
It definitely has a different year.
Revolution and
A year on the moon is not 365
So,
days. Okay, so find the distance of that geosynchronous orbit above planet X, given all that information. Mass of Earth you may use 6 times 10 to the 24th. What are the units? Kilograms. Radius of Earth you may use 6 times 10 to the 6th. What are the units?
meters.
Meters. How many miles is that about?
a lot.
It's like about 4,000 miles to the center of the Earth. It's like the distance from here to California. Surprisingly, it's not that. Okay, so I want you to find D. And then I want you to find the distance above the surface. You got to use Big Ugly here, don't you?
Oh yeah.
GMM over D squared equals
4 pi.
and 4 pi, that's Big Ugly from now on. So the period of planet X is 1/5 the period of Earth. The period of planet X is 1/5 the period of Earth. You may use, all right, can we do this?
Sure.
Do we have circular motion?
Yes.
Is the satellite moving?
Yes.
It's definitely moving. Geosync orbit just means it has the same period as the planet. Agreed?
Agreed.
It's the only way it stays up there. Looks like it's staying there, but it's moving with it. So immediately we go to Newton number 2. F equals ma becomes
FC equals MAC.
Fc equals mac. That becomes mass times tangential velocity divided by r.
And then FC equals
What's supplying this type of motion?
M4 pi squared.
GMM over d squared equals,
4 pi r.
you may leave, I'm going to be talking to myself, m 4 pi squared d over period squared. What can I cancel? The mass of the Earth and the mass of the planet?
Mass of the, well, it's the mass of the satellite and the mass of the
Mass of the
planet,
satellite.
not the Earth.
All right, I'll wait till you.
The mass of the Earth wouldn't even be in the equation.
I got
That's
2.7 times 10 to the 6 for this one.
For distance?
Yeah.
Of that above surface or center to center?
Oh, I forgot to subtract. Darn
I
it.
didn't subtract, so I'm
Ooh.
guessing,
Oh, well.
I'm guessing
Another
it's the
day.
center. That is subtract.
Another day, another mind.
So we got GMM over d squared equals m 4 pi squared d over tau squared. This r and this d, same thing. This is not radius. This is distance center to center. Don't get it confused with radius. I'm using r because almost every physics book in the world uses r. I'm not trying to confuse you. I just want to stay consistent. So we're looking for d. So we're cross multiplying. I see d cubed equals g, which is the universal constant. Mass of the planet X, this mass we canceled here was the mass of the satellite. So gm times tau squared divided by 4 pi squared. Okay? Tau is the period of the satellite, and the period of the satellite is the time for it to revolve around the planet. And because it's in geosync orbit, that time has to be the same as the period of the planet. And the period of the planet, I told you, was 1/5 the period of Earth. So you should be able to do this algebra. The period of the planet is 1/5 times 365 days, 24 hours in a day, 3,600 seconds in an hour. Crunch those numbers. 6.3 times 10 to the 6 seconds would be the year on planet X, would be the time that for planet X to make one complete revolution. That therefore it's the year on planet X, and therefore it has to be the time for the satellite to make one complete revolution. Okay? So that tau would go over here. So d cubed equals g, the universal constant times mass of planet X times tau squared, this number divided by 4 pi squared. Crunch all those numbers, the 8 meters. Now that d is the distance from center to center. Now if someone asks you how high does a satellite going to be, he or she is not looking from center to center. They're looking for how high above the surface is it. So the d from the surface would have to be that number minus the radius, which is going to be 5.2 times 10 to the minus times 10 to the 8 minus the radius of the planet. Where am I? Is half the radius of Earth, so that's 3 times 10 to the 6. That gives us about 5.09 times 10 to the 6, 2, 4, 6 times 10 to the 8 meters. So that's above surface. That is center to center. Okay? A couple important points. Make sure you get all these conversions okay. Mass of the Earth, radius of the Earth. You could go with those numbers. Cut the mass of the Earth divided by 3. So that would bring that down to 2 times 10 to the 24th. And the radius of the Earth, cut that in half. So that would be 3 times 10 to the 6. And the period, make sure you change years to seconds, because in the MKS system we only use seconds. So if I did the math right, you should get a distance center to center of 5.12 times 10 to the 8 meters, and a distance above surface of 5.09 times 10 to the 8 meters. Okay?